Hello, and welcome back once again to this tutorial model on logic designs, digital logic designs. So, in previous module, we talked about unsigned binary integers, which are either zero or only positive numbers or integers. Now, this time, we talk about and understand the basics of signed integers. So, signed integers, they will represent both positive and negative integers, including zero. So, there are three ways to represent signed integers. One is sign magnitude, as you can see on your screen here. Another one is one's complement, and the final one is the two's complement. So two's complement is the most efficient and the most used way of representing the signed integers. But in this module, we'll talk about the first one, that is signed magnitude. So as the name suggests, it has sign and it has magnitude. So this structure of, for example, of an 8-bit sign number will look like this. It has 8 bits. The MSB, most significant bit, is a sign bit, and the rest of the 7 bits in this structure indicates the magnitude of that number. So if the MSB of this 8-bit signed number structure, as an example here, it could be 16-bit, 32-bit as well. So if the MSB of that particular number is 0, we say the number is positive or 0. However, if the MSB is 1, then we say the number is negative. So it is very simple way of identifying whether that signed integer is a positive number or a negative number or a 0. So now, what is the range of values of these signed integers? So that depends upon the number of bits that we will use. But there is this formula. It will range of the signed integers is from negative of, in the bracket, 2 to the power n minus 1 to 2 to the power n minus 1 minus 1, where n is the number of bits that is used. So for example, it is an 8-bit number. So n equal to 8 here, and we will see that it would be, this formula would be minus, in bracket, 2 to the power n minus 1, that is 8 minus 1, 7 minus 1, to 2 to the power 7 minus 1. So it will start from minus 127 to 0 to plus 127. So you can see that 0 is also included. So you can now calculate the total values in this range is 256. So there are 256 numbers which can be represented using signed magnitude method. But if we compare the signed magnitude method or signed integers with unsigned integers, in the previous model with the unsigned integers, we saw we can still represent 256 numbers, but they were from 0 to 255. Here you have a limited way, 0 to 250 to 127, or from minus 127 to 0. So the range is half. But the advantage here is that you can also represent negative numbers. So that's why we take the advantage of signed integers. So this is the sign magnitude method. So now let's have an example what those numbers could be. We just saw the structure of using 8-bit example of a signed integer structure where MSB is telling us the number is positive or negative. Now the example. For example, Let's say this is the number 5 in decimal with a base 10 as shown, and its binary in 8-bit number system would be this as represented here. So of course, this is a positive number, therefore the MSB is 0. Or since it is 0 MSB, we say that the number is positive. Is negative way of representing the same number is -5, for example. What you need to do is you just flip the MSB. If it is 0, it becomes 1, and vice versa. If let's say you are given -5 and the decimal -5, its binary form is as shown right over here with MSB indicating it is negative number, and you are asked to determine the positive 5, then simply flip the MSB from 1 to 0. That gives you number 5, which is a positive number. So this is the positive integer, this is the negative integer. Let's say there is another example. So here you see that plus 45 is in decimal. The binary representation is 00101101. Of course, if you are asked to determine the negative of the binary of -45, so what you need to do, just flip the sign or flip the MSB. If it is 0, then it becomes 1, and vice versa. So this is how you are representing positive and the negative number. Now, as we just said, signed integer also contains 0. So let's say this is 0 in decimal, and the binary form is all zeros, the base 2 system. And if you are flipping the MSB here, then becomes 1, and the rest of the bits, which is the magnitude, remains the same. But then we say that it should be represented as negative of 0, that is -0. But how come? You see that you have no way to represent a 0 here. There are two ways to represent the same value, right? Negative and the positive. It cannot be the positive. It's a confusing thing. So in computer, you need a special hardware, for example, a comparator circuit or so, to distinguish between the positive and the negative zeros. If you represent or use this number system of sign magnitude to represent and use assigned integers. So you have to take into consideration that. So now let us finally understand this table. What you see here, I have values from 1 to 7, and then of course 0, or let's say 0 to 7. So total 8 values in the decimal, and unsigned representation of these values. So for example, 1, this is in 4-bit form now. I can also use 8-bit form, 16-bit form, 32-bit form, 64-bit form, and so on and so forth. So in 4-bit signed integer form and unsigned integer form, this table shows those decimal values represented. So for example, decimal 1, the binary form in unsigned is 0001. So this is a positive 1. As we just discussed right over here, to represent a negative form of the same number, for example, from 1 to -1, you look at the binary and look at the MSB and simply flip the MSB. So it is 0, it becomes 1, and other 3 bits, which is magnitude of that number, remains same. So the number 0001 is positive 1, but 1001 is negative 1. That is how you represent a signed integer, which is a negative number here. For number 2, your binary form of unsigned way is 0010, but again flip the MSB, it becomes 1 and other bits are same as the unsigned way. So it is -2. For number 3, flip the MSB, so it is from 0011, but number here is 1011. For number 4, then the binary form in unsigned is this, signed is again flipping the MSB. So similarly for number 5 and number -5, number 6, number -6, number 7 and -7. You see that how we are representing unsigned and signed integers. Finally, 0. Unsigned form, that is the positive 0, 0, 0, 0, 0. But how come when you flip the MSB for 0, it becomes 1, 0, 0, 0, that is -0. So 0 and -0. So you see that it is same as what we see here in the 8-bit form, which is kind of confusing. So this is something we need to address. So if you want to use this number system to be in use, you need a special hardware to, for example, comparator design to distinguish between the positives and the negatives zeros. So hope you found this small module useful of understanding how signed integers are used, what their range is, if it is 8-bit or 4-bit or 16-bit and so on, how to understand and represent positive and negative integers using signed magnitude system, number system. And with this table, you can have this 4-bit. So obviously, since you have used 4 bits here, the range, you can see that there are total 8 numbers, 0 to 7, that you could represent. Why? Look at the formula here. The range is from minus, in bracket, 2 to the power n minus 1 minus 1 to 2 to the power n minus 1 minus 1. So n is equal to 4 because you are using 4 bits here. Put in the value of 4 here. So this formula, after putting the value n equal to 4, it becomes 4 minus 1, that is 3, to 2 to the power 3 is 8 minus 1, that is 7, and here also 7. So final range is from -7 to 0 to +7. So here you see that from -7 to 0 to +7. So total numbers, you can see that the range is 0 to 7, 8, and these are 7 numbers. Total 15 numbers, 16 numbers that were represented using this one. So stay tuned for more engaging content like this. Until then, wish you happy learning.